In the previous examples, we looked at changes in the input values and changes in the output values as a result, and we came up with this formula using the approximation that the slope would be like delta y over delta x, and we rearranged it. However, what that's all about is just changes relative to a particular point. So if we knew our delta x and we wanted to know delta y, we would use the fact that the slope is a way to connect those two elements. However, in other cases, we might want to do that on a scale. So imagine our x value is here and our y value is here, and we actually pick a representative point, and we know the slope at that point. Can we then find some kind of formula for this entire straight line? Absolutely. It's just a simple extension of what we've already done. Returning to the advertising problem we've seen earlier, where revenue is a function of the advertising spend, with all the units being thousands of dollars, then we had an earlier statement we've analyzed, which was f prime of 200 equals 1.8, and that stated that the revenue will increase by $1,800 per $1,000 increase in advertising spending, or an advertising period. This other statement is much more clear-cut. This is if we spend $200,000 on advertising, then revenue is the output $1,500,000, or if you like, 1.5 million. So that's interpreting the statements that were given. How about using this to predict the effect of other advertising spends? Let's go back to one of the fundamental building blocks for straight lines. Linear functions have slopes, and this particular formulation here involves a point AC. X is A, C is the y value, and if we want to go through that point and have slope m, then this is the formula we're going to want. So let's draw this line here. Let's make it a negative slope just for interest's sake. This line here is y equals m x minus a plus c. So the key thing is it's a line with slope m and which goes through the point AC. And the slope is exactly what we had in our revenue model on the last page. Here's our point, and here is our slope. And so what we can say is that at the point A, advertising 200, we get a revenue C of this, and we have a slope of 1.8, so that 1.8 is our M. So if we put the 1.8 times advertising actual spend minus the amount we had defaulted to, the 200,000, plus the 1,500. Let's write that underneath with M x minus little a plus c. This is the y for a straight line. What we're expecting is that our revenue as a function of advertising, it's going to be close to this. So this is the key thing. This is approximate for R. We know the revenue is not going to follow this model forever, but if it follows it for small changes in advertising, that can be enough of a hint or an indication for what we might want to do as a strategy. This is the formula for the exact straight line. This is the formula for a straight line that's approximately equal to or very similar to what we expect the revenue to behave, as long as we don't change our advertising too much away from 200. The nice thing about this is we can actually predict revenue. So if we decreased our advertising to $190,000, we can predict what that's going to mean. Our prediction is that our R value is going to be equal to our slope. What we're putting in is the actual advertising we're going to spend with all the other ingredients relative to the 200,000 usual spend. That gave us revenue of 1,500,000. We calculate this through, we're going to get negative 18 plus 1,500, and that's going to give us $1,482,000, or 1.482 million. So our revenue will decrease, and the key thing here is that it decreases to, not by, it's not a relative change, it's actually to a new amount, to 1.482 million. And that is the power of having that slope information, is that we can make the predictions about the impact of small changes in our advertising choices.